I'm going to break this into two separate groups and look for a GCF in each group. Between these two terms, I notice that I can pull a 3 out, and I can also pull an x squared out, but I can't pull a y out. Even though there's a y here, there's no y over here. If I can't pull it from everybody, I shouldn't pull it from anybody. Thinking about what would be left behind, if I divided this by 3x cubed or took out a 3 and an x squared, if I want to get that 3x cubed back, I just need an x here. 3x squared times x would be 3x cubed. To get the negative 9x squared y back with the 3x squared, I would need a negative 3, because 3 and negative 3 would make that negative 9. The x squared would be taken care of, but I need a y chilling out inside of there to get 3x squared y. So that's a GCF. There's nothing in common between these two things. I'm confident that's correct. Moving on to the second group, looking at these coefficients, 2 and 6. The common factor there is 2. They don't both have an x, so again, I can't pull an x out, but this guy has a y, this guy has a y squared, so I can pull a y out of both. And then what's left behind? Well, I took this guy's 2, and I took his y, but there's still an x left behind. Even though the order would be different, were I to multiply these out, 2 times yx is the same as 2xy. That's just what's left behind. And then to get the negative 6 y squared with a 2y, I need a negative 3 to take me back to negative 6, and then to get back to y squared, we need another y. Then I'm happy to see that this and this are identical. They become a common factor between these larger terms we just created. So I'll take that common factor away from both of these pieces. And then what's left behind here is just this fella, 3x squared. And then what's left behind here is this 2y. And I will call that good.